Okay, square root of 5. Can we simplify that? There are no perfect square factors in that, so we're not going to do anything with that. I'm going to keep that up front right now. We're going to keep the 4. We're going to break apart the square root of 20. Perfect squares, whatever's left. What's the largest perfect square that goes into 20?
4.
And we're left with 5. Okay, what do we have here? We have 4 times this times this. 4 times the square root of 4 times the square root of 5. So we have minus 4 times what? Okay, that's perfect square. 2 times the square root of 5. And I'm just going to throw this in. Okay, so we get 8 square root of 5. Are they like terms? Okay, so we have one of these minus 8 of these. How many of these do we have? Negative 7 square root of 5. Isn't addition fun? Well, it's like an x. If you just see an x as an imaginary 1, right? It's the same thing. You treat these very much like variables. And there. Okay, we need to simplify each. There are 4 terms there to simplify. Now, you have a number out front. You keep it. Now the square root of 12. Perfect squares, whatever's left. What's the largest perfect square that goes into 12?
4.
Okay, 4 goes in 3 times. So we have 2 times square root of 3. So that's 4 square root of 3, right? That's just the first term. Now let's go to the second. We have 5 times the square root of 27. Perfect squares, whatever's left. 9 and 3. So that's 5. Don't skip steps. Square root of 9 is?
3.
So what is 5 times 3? We have 15 square root of 3. Please, initially, don't skip steps. I know you want to. Wait till you're good at it. Okay. 48. What's the largest perfect square? And it's not 4. And, you know, if you think it's 16, divide it by 16 and see. Did that go in evenly?
24.
Huh?
3 times.
24 isn't a perfect square, though.
3 times.
It is. It's 16. It is 16 times 3.
Minus 4.
Go ahead, Chelsea.
Minus 4.
Minus 4 radical 3. The statement radical 3 is correct. Square root is going to pinpoint it more. Okay, and this last one. Are there any perfect squares that go into 3?
Mm-hmm.
So we just have plus 2 square root of 3.
Okay.
So, first term, second term, third term, fourth term. Any like terms?
Yes.
All of them. So we want 4 plus 15 minus 4 plus... Wait, 4 plus 15 is 19. Minus the 4 we get plus 2 is... Okay, I was behind you. You went too
I
fast.
was just saying the 4, positive 4 and minus 4. Which are stuff
Okay. Let's go to the next one. Now we're getting into some heavy-duty variables, right? See what you can do. All right, I'll start by, I can try to write neater. We have 3, and then our perfect squares, and whatever's left, right? Are there any perfect squares that go evenly into 2? 2 is not a perfect square. None. What do we do with that 2 now? There's no perfect square. It goes on the right. How many y's can we stick in this first?
4.
Okay. We can only put even powers of exponents, variables there. What's left? All right, so we have 3 times, and what do we get here? This should always be All perfect squares, so you should be able to take the square root. Okay? Square root of 2y. Now let's go to the next term now. See, I'm going term by term instead of trying to do the whole problem at once, because I feel like you're less likely to get lost in the work. All right, we have 7, and then our radical. Perfect squares, whatever's left. Now look at 18. Are there any perfect squares that go into 18? Okay, 9 goes in. How many times? How many y's can we put? And what are we left with? So we have minus 7 times what? These are all perfect squares in here, so we should be able to take the square root. 3y squared. Square root of 2y. Okay, so we have 3y squared, square root of 2y, minus 21. We can multiply those, right? Okay. Do we have like terms? And you have to look all over. You have to look in here. Do we have the same? Ooh, yeah. That was a little dark. We look in here at the radicands. They're the same, right? They're both square roots, so they're the same. But then we have to look at our variables. We have y squared here, y squared here. They're the same. Now we can say they're like terms. So we actually have, God, I hope this isn't dark too. We have 3 of these minus 21 of them. So what are we left with? Huh? Yeah, negative 18. I was getting 17. Y squared, square root of 2y. Piece by piece, right? You have to be very procedural on this. Now I'm going to run into a problem of space on this next one. No, I'm not actually. I'll tell you why. Are there any perfect square factors there? Are there any perfect square factors there? Are there any perfect square factors there? There's no simplifying to do. It's a question of, do we have any like terms? Well, these two have the same radicand, but they're not like terms. Why? Yeah, this one has an x here, and that's missing here. This one has a different radicand. There's nothing you can do with that. You can't combine anybody. There's no like terms. It's like trying to combine x squared plus x cubed, right? You can't do it. They're not like terms. That's what you have there. They're just not. Okay. Let's look. You do nothing. You do nothing. I was just showing you that to show you that you can't combine them. As much as they looked a lot alike in a way, there were no like terms there. You can't do anything. That's why I knew I had enough space after I looked at it. Okay, this one here, I threw these last two in because they do give you some fractions, and I want to make sure you know what to do. First of all, these are like terms, and there's no simplifying, right? There's no perfect square factors there, no perfect square factors there, correct?
So sorry, what happens to the above one? It just stays there.
It just stays where it was. You can't. It's like if you had x cubed plus x squared. You can't put them together. It just stays. It's the same situation.
What would be right on the answer?
I wouldn't give you that. That was just an example to show you. I hate to break it to you, but you should be happy because half class will probably blow that. But it's just, you know, to give you. Well, anyway. Okay, are these like terms?
Yeah.
That 1/4 and 1/6 makes it look crappy, but they're like terms. Realistically, it's like saying if I had 1/4 x plus 1/6 x, what would I have to do to add them?
Like denominator.
Yeah, what's the smallest? What's the LCD here? 12. So I need to multiply numerator and denominator by 3, and we get 3 twelfths. That was a mistake. Yeah. Plus, and numerator and denominator by 2, and we get 2 twelfths x. 3 twelfths plus 2 twelfths is 5 twelfths x. But we didn't have an x, we had what? Yeah. So it's the same thing. We have 3/12 square root of 5 plus 2/12 square root of 5, and all those fractions in there, it's irrelevant to the fact that what we have is two like terms, and we add the coefficients. 3/12 plus 2/12 is 5/12 square root of 5. Am I really going to give you that? No. But you're going to see a little of it in your homework, and I don't want you to get blown away. Okay, we have to simplify these two radicals. Let's look at the first one. We have a fraction under the radical. What was the rule? If we have this, we do this. If we have that, we do that. Do you remember what we did? Then we separate, right? Is the denominator a perfect square?
Yes.
So let's separate. So we have the square root of 3 over the square root of 4. Well, that's the square root of 3 over 2. Great, no radical in the denominator. Plus, is 25 a perfect square?
Yes.
Separate. Square root of 3 over square root of 25. Well, it's almost the same. Square root of 3 over 5. And now it's one of those LCD situations, right? What's the LCD?
Okay.
Okay, numerator and denominator by 5. And we get 5 square root of 3 over 10. Numerator and denominator by 2. Just making me rewrite. Wait, going out of me. So we got 2 square root of 3 over 10. So what do we get? 7 square root of 3 over 10. Okay? Okay, I'm going to hit stop for 1